What if we did? Can you just do some game where you get ready to build food? Physics doesn't work that way, Mike.
Impact markers. We are in business.
I wonder how long that is so this doesn't
When the winter issue, not very long.
They do.
Yes.
By the fall.
I just got there. There's nothing else.
I'm done.
I've done this twice a year.
Yeah. And then you're yep. It just crazy.
Hi, Kyle.
And then 3, like half.
I got 3, 4.
Hey, let's do.
I say this to the same point multiple times.
That's good consistent.
I don't know what the rest of it is. Oh, here it is. We have one. Well, he didn't see it. He like ripped it up. So I had to write it.
The problem's coming. You can ask for help. I have solutions to most of them. You can also talk to each other for help. Yeah, I can't remember. Like, I think I said like we were going to turn them in this week or something like that.
I think it was originally today.
Was it today? Yeah, we're going to push that back. Push that back. Snowpocalypse or cold Mageddon or whatever you want to call it.
Mildly chilly.
Brisk. Yeah, so today we will finish off, well, chapter 25. We won't cover everything in chapter 25. The last little bit, I'm not going to do in lecture because a lot of that stuff we'll actually come back to when we start developing actual numerical relativity stuff, things like the conservation laws. So I will leave that out. But today we'll get through the core of what's in chapter 25 all the way up to linearized theory of gravity. Have any of you started on the chapter 25 problems? Yeah, one of them, the Newtonian limit, like we will get up to that today, but I won't actually talk about the Newtonian limit because I'll expect you to do it in the problem. And what I would have covered in lecture is way less involved in the problem is anyways, like you'll actually get more out of doing it yourself, but it's kind of cool. But we'll get right up to that point and we'll talk about weak field gravity. All right, questions before we get going? So we'll finish 25 today. Reminder that I'm out of town for the rest of the week, so we won't have class on Thursday. I need to update the schedule on the website, and I will do that. But next week, when we come back, next Tuesday, week from today, we are going to start with chapter 1 of Baumgart and Shapiro. So read chapter 1 of Baumgart and Shapiro. It is just a review of general relativity, and then touching on a couple things that we haven't actually touched on yet with regards to the physics of stars, like relativistic stars. But that's the only really new material there. So I'm not sure what I'll do with the schedule yet because we missed a day. I might try to compress some stuff from Baumgart and Shapiro. I don't think we're going to bother trying to make it up because let's be honest. I don't want to do that.
One thing on the schedule I noticed the other day, you do have lectures scheduled during spring break.
I do?
Yeah, week on March 4th.
Oops.
I mean, I'll be here. I would hope no one else is still.
So do I end early or did I just have an extra week of lectures stuck in there?
I think you copy and paste it because I forget
Well, you
what
have,
the topic was.
you have the same topic for all four
Yeah.
classes, so it looks like you just.
Oh, okay.
Either that
All
or
right.
the topic is.
All right.
classes.
That's a minor oops. That's not a major oops. I need to rethink my schedule. That's a copy and paste error. Okay. Geez, Steve. Bury the lead. All right. So look at this. You can still see the writing from the last time. They don't use the whiteboards. Recall from last time, the Riemann tensor, which encapsulates curvature of space-time. We developed this last time as an analogy of the Newtonian tidal gravitational field. And when we translated that into a GR framework, we ended up with this more complex, higher ranked tensor. Come on in, Howard. No worries. Which is the Riemann tensor. And in general, we can compute this thing, R, alpha, beta, gamma, delta. So it's a rank 4 tensor. It depends just on the metric, specifically derivatives of the metric. And so that looks as 1/2, and then a bunch of metric derivatives, G alpha beta, alpha delta, comma, beta gamma, plus G beta gamma, comma, alpha delta, minus G alpha gamma, comma, beta delta, minus G beta delta, comma, alpha gamma. So double derivatives of the metric. And since the metric has symmetry in its derivative, so G alpha gamma, comma, beta delta is equal to G alpha gamma, comma, delta beta. So it's symmetric in that derivative. The metric is, at least. We can derive certain properties of the Riemann curvature tensor, which allow us to simplify life a little bit. So, in particular, R alpha beta gamma delta is equal to minus R, which first slot, beta alpha gamma delta. All right, so it's anti-symmetric in those first two slots. R alpha beta gamma delta is equal to minus R alpha beta delta gamma, anti-symmetric in its second two slots as well. I think I'm capturing this on video. And then R alpha beta gamma delta is equal to positive R gamma delta alpha beta. So if you switch those both slots together, it's symmetric, not anti-symmetric. Okay? And then finally, one last property, R alpha beta gamma delta plus R alpha gamma delta beta plus R alpha delta beta gamma is equal to 0. You can get that from these properties if you do the gymnastics. Okay? So these symmetries reduce the actual number of free components in this. We mentioned this last time. You know, so all the Greek indices run from 0 to 3. So there's really 256 possible components of the Riemann curvature tensor. But these symmetries reduce those components to just 20 that are actually independent, which is manageable. It's still a lot, but it's manageable. And then in general, so I won't go through the stuff about the Weyl curvature tensor, but in completely arbitrary basis, so not necessarily a local Lorentz frame, and not necessarily a coordinate basis, okay? So the commutation coefficients won't necessarily disappear either. I can write the Riemann curvature tensor with the first index raised, and so I've used the metric to do that. Alpha, beta, gamma, delta, like that. is, in a completely general basis, dependent on derivatives of the connection coefficients as follows. Gamma alpha beta delta comma gamma minus gamma alpha beta gamma comma delta plus gamma alpha mu gamma gamma mu beta delta minus gamma alpha mu delta times connection coefficient gamma mu beta gamma minus connection coefficient alpha beta mu. Oops, where's my eraser? Where is the eraser? That last term depends on the commutation coefficients. So there's that connection coefficient times the commutation coefficient C, gamma, delta, upstairs, mu. So that's the general form. So we've got some derivatives of the connection coefficients and then some basically dot products of them, right? Where we're summing over the repeated indices mu in all of these terms to get back down to the right rank, right? This, to do by hand, is a nightmare. It is not fun, right? Which is why I asked you all to look into software last time so that you can compute these things. And you all found some decent looking stuff, both in Python, which seems pretty usable, and then Steve went and just wrote his own Mathematica code. Did you share that, by the way? You put it on the Slack channel. It's on the Slack channel. And all of you can get a Mathematica license through MSU if you want to use that. But in any case, use software to compute these in a completely general basis. Right? There's certain cases where life is easy and you can compute them somewhat trivially. But for arbitrary bases and when we actually go to do numerical calculations, you're just going to want to have software do it for you. Okay. So now, on we trudge. So that's the Riemann curvature tensor and some properties of it and how it depends on the connection coefficients. Let's talk about something called curvature coupling, as well as the equivalent principle and various laws of physics in curved spaces. All right, so let's consider the stress energy tensor for a perfect fluid, which we derived in one of the homework problems. So it's very familiar. T rho plus P times U, tensor product, U. These are the four vectors plus P metric tensor. All right, so there's our stress energy tensor for a perfect fluid. This is a frame-independent geometric relationship, right? And it is a non-gravitational law of physics that we derive in special relativity, right? So it obeys all the laws of special relativity, like the special version of the equivalence principle, right? But it is in the context of a global Lorentz frame, right? So how do we re-express this then in the framework of general relativity where we can only allow for local Lorentz frames? That's the question, okay? So it turns out that the equivalence principle actually tells us that the form of this relationship, the form of the stress energy tensor for a perfect fluid in GR looks identically the same as the special relativistic version, right? And that's for the same reasons that we derive some of the other relationships in general relativity compared to special relativity in chapter 24. I can arbitrarily pick the origin of my coordinate system, right? I can put it on the world line of some particle that's in free fall, for instance, right? Or some fluid element that is a perfect fluid. I can choose to have the coordinate origin of my local Lorentz frame on the world line of that particle. And then there, where the metric is essentially flat, I can derive these things. But since there's nothing special about that particular location in space-time, it must be true at all locations in space-time, right? And so using that sort of same mind meld trick, we can say that the form must be the same. So what changes in GR then? How is this then actually different in GR compared to special relativity?
Is it identically the same? What is one of the key differences mathematically between GR and special relativity when you're actually doing calculations?
For bases,
You allow for completely arbitrary bases, but the metric, right? It's no longer the flat metric. And so while the form of this equation is the same, this is no longer the flat metric. And so that's where general relativity comes in, right? It is more or less the same. So that goes back to our principle of special relativity versus general relativity. Special relativity essentially encompasses all classical physics for non-gravitational laws, right? So if there were no gravity, we'd be good. This would be true always, everywhere, in all things. If there were no gravity, right? So special relativity covers non-gravitational laws. General relativity is, deals with the gravity. Okay. So this is true then for all physical laws that include gravity even, that can be expressed as local relationships, right? This stress energy tensor is a local relationship. There's nothing global about it. But now recall for momentum conservation. To derive that, we need to take an integral around some surface of some volume. So I've got some volume in space-time. I've got a surface around that represented by partial V. And then I need to integrate the stress energy tensor around that surface, right? And I'm going to say that this is equal to 0 in order to have conservation. We did this in special relativity. You can derive this precisely in special relativity, and from it, you can get conservation laws, which look very much like Euler's equations, right? In the end, right? That we're very familiar with. It's just relativistic versions. But can I do this in general relativity using this form of the stress energy tensor? Remember from? No. Why not? Because the integration is not well posed, right? Because the integrand here, if you count the slots, there's one open slot, so it's a vector, right? And it's a vector on that surface bounding the volume, right? And our vectors, remember the way we redefine them on curved manifolds, are things that live in tangent spaces. And in order to actually compute this integral and sum up all the little contributions from all over, I've got to parallel transport all those little vector contributions into the same tangent space so that they can be on a level playing field and get added together, right, to compute this integral. But now the paths that I take for those transport of those vectors to new parallel tangent spaces is not clearly defined. I can do it in an infinite number of ways, essentially, and the path that I take to do that transport will change my answer on a curved manifold. Not on a flat manifold, but on a curved manifold. So this is not a well-posed problem in GR. Another way to look at that is that this is not a local law of physics. This is global, because now I've defined some large, not infinitesimally small space that I'm integrating over, right? And so these non-local laws have trouble translating from special relativity to general relativity. Okay. And so in this case, the equivalence principle doesn't hold, right? So that's problematic. Okay. Another one that is also problematic, and this is true for any not completely local law of physics, like I said, is spin angular momentum of some particle. So think about spin angular momentum. Another thing that we generally consider conserved. In this case, I'm going to represent that by S sub I. Here, in order to compute the spin angular momentum, again, I have to take an integral, right, over the interior of the body of whatever thing that I want to compute the angular momentum for. So over the interior of whatever this thing is. And I'm going to do, remember, angular momentum involves a cross product, so I have to have my Levi-Civita tensor in there, IJK, coordinates, xj, stress tensor, k0. This is the momentum, right? This is momentum. And then integrating over the volume. Okay? So now, where these are the, just to write it out, that guy is momentum density, just to refresh you, for the components of the stress energy tensor, right? And that's a curl. Just a curl. So this actually works fine in GR if it's a point particle. So if I'm considering the spin angular momentum of something that is an infinitesimal point particle, it's fine. Why? Why now all of a sudden can I apply the equivalence principle if it's a point particle? That it's local, and it's specifically at the origin of my local Lorentz frame where the metric is flat, right? So it exists only at the coordinate origin of the local Lorentz frame. And remember when we talked about Fermi coordinates, right? There was those high order terms as you got away from the origin that changed the metric away from flat. They changed the connection coefficients away from 0, right? Same deal is going on here. This is what's entering into these equations when I have to do these integrals over some finite space-time volume, right? I get away from that coordinate origin of my local Lorentz frame, and I get these extra terms creeping in that make the metric not flat, and all these problems with curved manifolds enter in, okay? So with this, in special relativity, I can write down a conservation law for the spin angular momentum. S, I guess that's a tensor, or a vector. Okay, so that just means that along whatever particle thing that I'm considering, along its 4 momentum, the spin angular momentum vector is parallel transported. That's what this is. This is a law of parallel transport, okay? Along the world line of that fluid element or that particle. Same deal with this law over here. It's not a well-posed integral in general relativity in a curved spacetime. And so I can't pull the same trick. And so it's also, for the same reasons, not very well posed. Okay? And specifically the reason, if you get into this particular case here, is that for a finite-sized particle, the coupling between the curvature of the spacetime, for a curved spacetime, and the particle's quadrupole moment, essentially, causes a torque to be exerted on that particle. Okay, so spin angular momentum, right? It's represented by some vector. Right? And if it's parallel transported, that vector is conserved. But now, how do I change the spin vector of a particle? Generally, not a trick question. Apply a torque, right? And so if this thing has some finite extent, and it's trying to be parallel transported through some space-time that actually has a curvature, what happens is that, in effect, you get a torque on that particle, which will change the direction of its, the direction and magnitude of that spin angular momentum vector. And the way that looks is, in general relativity, so now I'm going to write things in everything in terms of 4 vectors. So S alpha gradient with respect to mu, u mu, that's the directional derivative, right, along the world line, is equal to Levi-Civita alpha, beta, gamma, delta. This is the quadrupole moment tensor. Where's my eraser? It's an I with a little line through it. We're running out of symbols. So this is the way we're going to do this one. And the book, they use like a curly I, but in the literature that I tend to read and write, we often represent it with this little I with a line through the middle. Lost my place. Okay, now comes in the Riemann tensor, right? R mu nu delta gamma, u delta u upstairs nu u upstairs zeta. Sorry, okay, so index lining, I was lining up my indices and something didn't make sense. This is not a delta, that's a zeta. Just to cancel out my indices. Now it's all right. Right? Okay, so looking at this, what does this imply? If there is no quadrupole moment, there is no torque. Yeah? Question? This is precisely where my notes got cut off. And so that must be, right? Because the only index that I should end up with in the end is an alpha. And so, okay, so now tell me, so what should the indices of the Levi-Civita, what should they be? What am I missing?
The mu is also, no, wait.
Mu cancels there, beta cancels there, the zetas cancel there, the deltas cancel there, the nu cancels there.
There's 3 deltas.
There's 3 deltas.
Yeah, you got one in the Levi-Civita.
Or is it a zeta?
I think it should be a zeta, right?
No, because your zetas cancel.
So this is where my notes cut off.
Yeah, delta.
Hold on. I just wrote it wrong in my notes. I'll fix this. Hold on.
First, you could have a gamma.
I just wrote it wrong in my notes. Let me verify. I think we can figure it out, but let me just verify.
Consider that first unit. So,
So it looks like the delta is after the Riemann tensor. Both seem like both are down.
they are both down. One of them should be a gamma.
There's the equation. All right, let me fix this. I'll have to go back and fix my notes. Alpha, beta, gamma, delta. That's what the notes have for the Levi-Civita. Alpha, beta, gamma, delta. And then beta mu, R mu, nu, gamma, zeta. I erased the wrong one. Yes, now that works. Now that works. That was the fix. Sorry about that. And let's see. I had that wrong in my notes. All right, I'll go back and fix that. Update my notes. Okay, so thank you very much. But what this means is that, remember, the Riemann tensor represents curvature of space-time, right? That is coupling to the quadrupole moment of the body that we're considering and causing a torque. Well, it causes this to be non-zero, meaning that the spin angular vector, angular momentum spin vector, is not conserved along the world line, right? So this is a torque. And if there is no quadrupole moment in the body that we're considering, there's no torque either, right? And so if it's an infinitesimal point, it can't have a quadrupole moment. Another way to get at that requirement that this applies for point, doesn't apply for point particles. Okay, there's sort of a real world representation of this, which you could actually derive from Newtonian gravitation. But the Earth, Moon, and Sun system have a net quadrupole moment, right? And because of that, the Earth's coupling, and the Earth has a quadrupole moment, so the Earth is not a perfect sphere. So if a perfect sphere doesn't have a quadrupole moment, right, you've got to have some distortion from that to get some quadrupole moment. But the Earth rotates, and because it rotates, it's slightly flatter at the poles and at the equator than it is at the poles. It's slightly oblique. So that induces a quadrupole moment. And now, because of this curvature of the space-time, caused by the Moon, Earth, Sun system, the gravitational field is not perfectly smooth, right? That causes precession of the poles of Earth. And it's precisely a result of this curvature coupling phenomenon. You can solve that Newtonian, but it also falls out from this part of GR. Okay, so when does such curvature coupling like this matter? Rule of thumb is that when the physics you're concerned with involves double gradients. That's the rule of thumb. If there are double gradients. Why is that? Okay, so recall in a local Lorentz frame that the connection coefficients, the gamma, alpha, beta, gamma, delta, equals 0 at the origin, right? They're 0 at the origin. But now, gamma, alpha, beta, gamma, delta, comma, mu is not 0 at the origin. So the gradient of the connection coefficients is not 0 at the origin. So if I involve any physics that requires me to take a double gradient of the metric, remember the connection coefficients, they generate, in a sense, the gradient in an arbitrary basis. If I've got to do that twice, I bring in gradients of those connection coefficients. And so all of a sudden, even in a local Lorentz frame, I've got these additional terms due to curvature, which are going to matter. And you almost know this from what we know about just classical mechanics, right? Anything that involves a double gradient. What's something from just Newtonian mechanics or classical physics that involves a double gradient? The wave equation, right? And is that a completely local phenomenon? No, right? It's an elliptic equation, right? And so that can't be expressed in a completely local form. It involves global integrals to solve it, right? If you were to turn around and try to solve what the scalar field was or whatever you were sticking into the wave equation, you'd have to do some global integral to solve that equation. The Laplace equation, exactly right. Yeah, yeah. You're right. The wave equation is hyperbolic. I was thinking Laplace. Also involves double gradients, though. So, like just Newtonian gravity, right, where you've got a Laplacian of some scalar field, is what your gravitational field is, and some source function. That involves global integrals in order to solve it for what the gravitational potential is. Right? So it's not a completely local law. The analogy here holds for general relativistic stuff. Okay, so now, also in my local Lorentz frame, because of this, the gradient of some vector is going to be the same. So if I've got some A alpha comma beta, this is just going to be partial A alpha partial X beta. This is true in both general relativity and special relativity because of this. And remember the way that we define gradients, right? They come in to this full gradient. Well, the connection coefficients do. They come in as a term representing the either non-orthonormality of the basis or curvature of spacetime. But now, if I've got to keep going with this, those derivatives of the connection coefficients don't vanish. And so if I were to take this spatial gradient again, I would end up with terms that depend on the spatial gradient of the connection coefficients, and those are non-zero in GR, even in a local Lorentz frame. And so now I can't just elevate my special relativistic laws of physics to GR in the way that we did with the stress energy tensor. Just pretend it's the same. Can't do that anymore. Okay, so for instance, now here comes the wave equation, which we were just talking about. Wave equation, right, and E and M, so just electromagnetic wave equation, where we've got a vector for potential. So again, special relativistic. Okay, and in special relativity, that would look something like this. A alpha, semicolon, mu, mu, right? So that's a double gradient. Everything after the semicolon implies differentiation. So both of these mu indices are differentiation. one on top, bottom, they're repeated. That's Laplacian, right? That's just a Laplacian operator. Is equal to 0 in special relativity. But now in GR, we won't derive this, but you can get to it. I mean, this is somewhat straightforward, just involves working out the definition of the gradients. In GR, we've got this same left-hand side, but now on the right-hand side, it's no longer 0. I've got something that depends like the Ricci tensor alpha mu and vector potential mu. So now, the nature of the wave equation is completely different. It's not 0 anymore. Got some terms that depend on the curvature. In that case, the Ricci curvature. Okay. So that's curvature coupling. Take care. That's right, the job talk, right? Good luck to the candidate. My notes are already posted, and I'll post the video for this if you care to see it as quickly as I can. Okay. So now let's move on to maybe one of the last things we'll talk about, Einstein field equations. I'm going to do this. So the book calls it one equation. I'm very used to calling it equations because they're tensorial, and so there's an equation for every component. But the book makes it singular, and I trip over that every time I read it in the book, but that's fine. So Einstein field equations, or equation. Okay, so through equations like this, and when we were talking about the geodesics of free fall particles, and several other things that we've done so far, we've seen how curvature of space-time can make particles move, right? We've seen how that can happen. In other words, we've seen what effect gravity can have on particles to make them move. But what we haven't talked about at all is what makes space-time curve, right? How do we get and write down laws that, that actually describe why space-time would curve in the first place, right? It must be related to the stress energy of fluids, of particles, of gravitating bodies, right? Like just from analogy to Newtonian mechanics, we know that mass gravitates, right? And so right from the get-go, Einstein knew that, well, mass in some way must be generating curvature of space-time. And so finding that relationship, that closed set of equations that obeys and describes how matter causes space to curve and how curvature causes matter to move, was challenging. And it tripped Einstein up for a while. But one approach to this, which Einstein took, and many, many, many others took, was to start with Newtonian gravity, right? Because we know that Newtonian gravity works pretty well in most contexts, right? You know, apples fall at the same rate when they hit you in the head. And so starting from there, we can use Newtonian theory as guidance for deriving our relativistic version of gravity. And so this is, you know, the Newtonian gravitational law, right? Laplacian of some scalar field, which is the gravitational potential, is equal to 4 pi g rho, where rho now is just the mass density. Before we've used it as the rest mass energy density, but this is just mass density now in the case of Newtonian physics. We can rewrite that Laplacian in terms of the tidal field. We did this before, okay? So we can say that tidal field tensor EJK is second partial derivative with respect to xj, xk. We did that before when we were trying to make a connection between Newtonian and general relativistic gravity, right? So this is the tidal field tensor. The Newtonian version of it, okay? So that means just looking at this and making an analogy between these two, this is a second spatial derivative, but if I wanted to create the Laplacian, the way that I would do that is E, J, J, right? Sum it up, repeat the indices. And so then just looking at my equation up there, I can rewrite the Newtonian gravitational law in terms of this tidal tensor. Now, why would I do that? We've already made an analogy between Newtonian gravity and general relativistic gravity through the Riemann curvature tensor, right? The Riemann curvature tensor is the general relativistic equivalent, by analogy, of this tidal field tensor, right? Okay. So what's that get us? We can then sort of say that this tidal field tensor in Newtonian gravity is completely determined by the gravitational potential, right? Once I know the potential, I know everything about gravity, according to Newton. So we might correctly surmise that the Riemann curvature tensor then, by analogy, depends only on the metric. I'm going to increase the rank of everything by 2. So my scalar field goes up to the second rank metric, and my second rank tidal curvature tensor goes up to the fourth rank Riemann curvature tensor. Okay, so that's just by analogy. Okay. Okay, and we also worked this out last time or the time before. It's been so long now because of the skipped class, that I can express the Newtonian tidal field as certain components of the Riemann curvature tensor, J0, K0. We worked that out. Didn't we do that on the board? I think we did. Okay, so now take the trace of this, which will give us, right? So this is just the trace. Where did I go? Alpha 0, alpha 0, to take the trace of that. Had to raise an index before I did that, but I can rewrite the trace to just like that. Which is just R0, 0, since R0, 0, 0, 0 is equal to 0 by the symmetry relations of the Riemann curvature tensor. By symmetry. Okay. So now I'm looking at this and I go, well, that. So what if I took the time component of the Ricci tensor, which is contraction of the Riemann curvature tensor, and I said the following? Well, R0, 0 equal to 4 pi G rho. Based on what we've derived before, this seems like it must be true. Okay. Which is it's not a bad guess for a starting point for the general form of the field equations. But this is written in a component basis. What do we need to do to make this completely general? We need to be able to write it in some way that's completely basis independent, right? In a coordinate-free form. In other words, we need to write it in a way that it is a geometric object, right? In a geometric relationship. We need to elevate this up from its component roots to something completely general. And just like so, remind yourself that T00, the time component of the stress energy tensor, is about equal to rho, especially if, and this is the mass density, if my spatial components of my of my 4 vector are much less than 1. In other words, if things are moving really slowly, the energy density, which is the time component of the stress energy density, is just the rest mass density. right? Remember, 0, 0 of the stress energy tensor is the energy density, but that includes rest mass. If the thing ain't moving very fast, its rest mass is much greater than its kinetic energy. So this is about true, okay? So looking at that and going, okay, well, maybe the form of my equations is something like this. R alpha beta, that's the Ricci tensor, 4 pi g t alpha beta. You're just trying things at this point to see if they stick. And that's kind of the approach that was taken, was to try things and see if they stick. Now, this is not a bad guess for what the field equations are, but there's problems with this. If you go through these equations and you eliminate all the various components of these equations that you can eliminate with symmetries, both of the Riemann tensor and of the stress energy tensor, you end up with 10 independent components, okay? I'm doing a lot of arrows today. I'll do something else. Star. 10 independent equations. Okay? The problem is that there's only 6 unknowns represented here. Why is that a problem?
It's overdetermined.
It's overdetermined, right? That's not good. We need 6 equations and 6 unknowns, so we need to find a way to eliminate 4 of these equations. And this tripped up Einstein for a while. And it wasn't until about 1915 that he was actually able to figure out a trick to get it right. And the book talks about this, and it references a more historical book by Peiss. Hilbert, like of Hilbert, Space Hilbert, figured it out at the same time. And he had talked to Einstein about Einstein's struggles with solving this, and he went off and figured it out independently. Dirty. But it happens. But they figured it out at the same time, more or less. And you know what? We don't call these the Hilbert field equations, do we? Hilbert got enough. Okay, so the trick is the following, all right? What you do is you say that, okay, what if it's not the Ricci tensor over here, but some other second-rank tensor? I'm just going to say it's some other second-rank tensor that encapsulates the curvature. And I'm going to say that it is related, basically I'm going to say this. Assume the field equations have the following form. G alpha beta is equal to kappa T alpha beta, where I don't know, this is a constant, okay? So that's a constant, kappa. And I don't know what it is. And I also don't actually know what the exact form of this is. I know what the Ricci tensor is. I can express that in terms of the metric, right? I'm going to assume that this depends ultimately only on the metric as well, but I don't know how yet. But this is the form of my field equations that I think they must take. And I'm going to require that this new curvature tensor is divergenceless. In other words, G alpha beta semicolon beta 0. We could even make it by definition. I'm going to require that it has that property. Okay? Now, I already know from before that, well, this is actually a property of the local version of 4 momentum conservation, right? The divergence of the stress energy tensor is 0. That's from local 4 momentum conservation. Great. So now I've got these 2 tensors that are related to each other by some constant, and I've got some properties of them. They're both divergenceless. So I can then say that if I take both of them, bring that thing over to the other side, G alpha beta minus kappa T alpha beta, and then take the divergence of that, what must this be? Yeah, sure. Cool. All right. So now I can actually use that. So if you look at this, I've got this divergence of this quantity. It must be 0. That is essentially now an extra set of constraints on the system. And if you do the counting, repeated indices, the betas go away. So I end up with just one index in alpha, 0, 1, 2, 3, 4, or 0, 1, 2, 3, which is 4. And so these are 4 equations which eliminate 4 of these independent equations. Now I'm down to 6. So now, with this form, requiring this, I can actually have a not overly constrained system. I eliminate those 4 extra equations due to requiring this. Okay, cool. So then, the derivation of this is a bit more involved, so we'll just write it down. It turns out, this is one of these crazy things to do, is just say, it turns out that the form of this curvature tensor is the following. R alpha beta, the Ricci tensor, minus 1/2 the curvature scalar times the metric. So if you recall, I just erased the old guess at the field equations. This would have been the old field equations. So in order to eliminate those extra 4 equations and to make this divergenceless, we have this extra term. Okay? And again, this thing is divergenceless by construction, right? And we're going to call this now the Einstein curvature tensor. Some sense a rearrangement of the Riemann curvature tensor. But now this is the curvature tensor that satisfies our requirements for the field equations. What's this tell us? This now relates the curvature of space-time, represented by the Einstein curvature tensor, to properties of the matter, of the energy in the system, right? The stress energy of the system. So now I can tell you, this is why things gravitate, right? For things that are gravitating bodies, here's how they cause curvature of space-time, right? Plop some arbitrary stress energy into the system, and you can solve for the curvature tensor, which tells you how space should be curved, right? But I still got that pesky kappa. I need to know what that kappa is. I would like to know what that kappa is if I actually want to do any calculations with this. So how do you think we might go about solving for that kappa? It better agree with the Newtonian limit. So I take my equations. I know that it's got a boundary condition, right? At low enough field strength and at low enough speeds, it better match up with Newtonian. So take that limit and then solve for my kappa constant, okay? So writing out the field equation now in terms of the Ricci tensor and the curvature scalar, R alpha beta minus 1/2 curvature scalar G alpha beta is equal to kappa T alpha beta, right? So we have before. I can take the trace of this to figure out what the curvature scalar is, okay? So taking the trace, say that, take the trace, which gives me R is equal to minus, right? Yep, minus kappa G mu nu T mu nu to get the trace. That determines the curvature scalar. So I'm going to take this expression now, stick it back up into here for the curvature scalar, and solve. All right. So that leads to R alpha beta is equal to kappa, pulled it out, all times T alpha beta minus 1/2 G alpha beta G mu nu T mu nu. Like that. Okay. So now, in the Newtonian limit, how can we simplify this? One, I've already said this. T00 is about the rest mass density, and that is much, much greater than the momentum densities, right? Because it's slowly moving. We're assuming that it is slowly moving. Similarly, the rest mass density is much, much greater than any stresses acting on the fluid. We have to assume that as well. That's true in the Newtonian limit, otherwise things get relativistic. So, considering only the time-time component, right? Which remember, thinking back to when we had the Newtonian expressions, the analogy and the connection we made was only T00, right? Only that rest mass density. So, taking just the time component of this equation, R00 is equal to kappa T00 minus 1/2 eta 00 eta 00 T00. Why did I switch my G's to an eta? This is Newtonian limit, it's got to be close to flat, right? So I can assume that I have a flat metric. This is equal to 1/2 kappa T00, right? That's just, I can do that math, right? Because these components, right, they're 1. And so that's just equal to 1/2 kappa rho. Okay. Now recall, did I erase it already? What did we have before for my guess? Where'd it go? Right. So we had before, when we were guessing, R00 equal to 4 pi G rho, right? And so kappa, equating those two things, is 8 pi G. Okay? Oops, skip page. Therefore, the final set of equations, therefore, G alpha beta, Einstein curvature tensor, is 8 pi G T alpha beta. And those are the Einstein field equations. That's it. We can do one more simplifying trick. It's not really a trick, but we can make our life easier. And, you know, I feel like this is the slow initiation into a mystery religion, where you're slowly taking various rites and learning various secrets and becoming part of the club. So to become truly a relativist, you will pretend like all these constants are 1. We've already made C 1. Right? Speed of light's 1, right? Well, now that we've got gravity into our relativistic framework, we're going to make G 1 too, because that's just annoying and it's confusing. And it's Newtonian. And also, the value of this physical constant is extremely poorly constrained experimentally. So let's just pretend it's 1. No problem, right? And so the final step, geometrized units. We already had C equals 1, so now we're going to say G equals C equals 1. Which is the crazy thing, right? If you make them both equal to 1, then they're equal to each other. And this actually implies that 1 is equal to G over C squared, which is equal to 7.42 times 10 to the minus 28 meters per kilogram. Or in other words, I'm going to say that 1 kilogram is equal to 7.42 times 10 to the minus 28 meters. I have now decided to express mass in distance. The mass of the Earth is 4 millimeters. The mass of the Sun is 1.5 kilometers. Relativistically, what do you think that's pretty closely related to? Schwarzschild radius, right? So if I took the mass and squished it down to less than 1.5 kilometers in radius, black hole. Which is fun, right? Okay. So now it's at this point, we can write these completely frame-independent equations in the way that you'll often see them expressed in geometrized relativistic units. That's it. I've gotten rid of the G to make my life easier. There is a table in your book for converting various constants and units to geometrized units for your convenience. That's it. We're there. You've taken your first step into a larger world, right? All right, questions? Let's talk about some useful things that we can do now that this is gravity. This is it. It's fully determined. 4 weeks of effort to get to that equation. Okay, but now let's talk about weak fields and what we can do in that limit. So obviously a weak gravitational field limit is going to be the Newtonian limit at some level. That's a problem that you're going to work on. All right, that's one of the problems that's assigned. So here, by weak is to say the following. There is almost a global Lorentz frame. So in general relativity, we can only assume a local Lorentz frame. In special relativity, we had a completely global Lorentz frame. And the weak field limit, we could almost treat everything as globally Lorentz. Almost. Okay? Mathematically, we're going to express this as the following. We're going to take the metric, G alpha beta, and we're going to set it equal to the flat metric plus some correction. Okay? Plus some correction H alpha beta. And we're going to require that this H alpha beta, the magnitude of its components, are much, much less than 1. This is the longest H ever. Okay? Now, in this weak field limit, from whence we can derive lots of fun stuff. If you want to get to the Newtonian limit, you've got to satisfy 4 constraints, right? One, the magnitudes of these things of, let's say, the correction to the metric, the time derivative of it, its magnitude, has got to be less than the magnitude of its spatial derivative. Which is to say that this correction to the flat metric varies much more slowly in time than it does in space. Okay? So the gravity is changing slowly in time. A byproduct of that is, and I don't think I wrote that down in the notes, and I meant to, but I remember it. A byproduct of this is that the proper time is roughly the coordinate time. So remember that difference we have between proper time and coordinate time. So in this case, where the time derivative of H alpha beta is small, coordinate time and proper time are about the same. And so we return to this concept of universal time that we had in Newtonian theory, right? We had to dispense with that to talk about special relativity. But here, because we're getting the Newtonian limit, we return to a sort of concept of universality of time. Okay, so that's one step towards Newtonian. 2, the magnitude of the momentum density has got to be much, much smaller than the energy density, which here I'm going to confuse you, and I'm going to switch back to calling rho the energy density, not just the rest mass energy density, but the total energy density. Okay, that's the time-time component of the stress energy tensor. So what this says is that stuff is moving slowly, right? Motions are slow. They do not approach the speed of light. 3, basically the same thing is that the spatial components of the four velocity are much smaller than the time component. Okay? Which is another way of saying that any particle that is moving under the action of gravity is moving slowly. Where might this break down? Maybe a black hole, right? Their gravity is so strong that any particle, even in free fall, would approach the speed of light. But Newtonian theory is very bad for treating black holes, it turns out. So that's fine. We're on our way to Newtonian again, right? And then finally, we're going to make the assumption that stresses are, by the same token, weak. Right? They've got to be. They've got to be. If you can satisfy all 4 of these things, you can reduce general relativity to Newtonian theory, starting from the field equations. That's one of the problems. Right? Okay. Good. Good, good, good. Questions? What's the next thing? Right. This will be the last thing we do today. And I think we'll end at a nice spot to then transition to the other textbook. And just note that there's a couple more chapters about general relativity in Thorne and Blandford. They get a little more specialized on their topics. And if you want, go take a look. Remember, I posted to the Slack channel all of the chapters from Thorne and Blandford with a preprint. And you might look at those as reference as we're going into numerical relativity, but most of the stuff in those chapters is covered in some way in the numerical relativity book, so I thought here would be a nice place to stop and transition. But feel free to look back at those chapters for some of this stuff. Last thing we'll do from Thorne and Blandford is linearize theory. And our starting point for this will be that metric perturbation equation, where h alpha beta, the magnitude of it, of course, is much, much less than 1, right? And since that's small, I can develop a theory which is linear in this h alpha beta, right, that describes gravity in the weak field limit. And that can be pretty useful. Okay, and in that case, h alpha beta is, in a sense, a gravitational field, right? Because curvature is still causing things to move under the action of gravity. And if everything were flat, there would be no gravitational accelerations, right? And so I'm going to treat h alpha beta like it is a gravitational field in flat space-time. So this, in a sense, is special relativity, right? This is special relativity plus some gravity. It's not too dissimilar from some approaches that were taken to transition from special relativity to general, but those never really panned out. But if you start from general, when you've got the correct theory of gravity and then linearize it, you can actually end up with something that is a lot like special relativity, where you can treat the laws of physics as though they exist in a flat space, and then there's some gravitational field which is acting on things to make them move. You can do that. And get something kind of useful out of it. Okay. So now, let's do that to some extent. So recall, in this case, I already wrote the Riemann tensor up at the very beginning of class. And remember, it depends on second derivatives of the metric, bunch of them, right? So if I take that, stick it into my expression for the Riemann tensor and work it out, these derivatives are going to disappear because it's just the flat metric. I'm going to end up with something that only depends on the derivatives of my correction to the metric, h alpha beta. So that looks like this. R alpha beta gamma delta is equal to 1/2 h alpha delta comma beta gamma plus h beta gamma comma alpha delta minus h alpha gamma comma beta delta minus h beta delta comma alpha gamma. Right? That's just the expression we had before for the Riemann tensor, but now I've substituted in this expression. These derivatives go away. It just depends on that correction to the flat metric. And Einstein tensor is then going to be G alpha beta, which we've defined as R alpha beta minus 1/2 curvature scalar times the metric G alpha beta. Using the definition for the metric there, our definition for the Riemann tensor here, I can stick those things in here and get an expression for the Einstein tensor, which looks something like this. I'm going to bring a 2 over here. 2 times G mu nu, oops, downstairs. G mu nu is equal to H mu alpha comma nu alpha. And both of these indices are differentiation indices because they follow a comma, plus H nu alpha comma mu alpha minus H mu nu comma alpha alpha minus H comma mu nu. This is a scalar. It's the trace of my metric correction. Minus the flat metric mu nu times H alpha beta comma upstairs alpha beta minus H, that's the scalar, comma beta beta, like that. You're thinking, that doesn't seem easier. We're going to get there, okay? But that's just plugging those into here, working out the math, using the metric of raise and lower indices as needed. Okay, now I know from the field equations that this is equal to 16 pi t mu nu. I just brought my 2 over, right? That's where it went. I know that. Okay. Also, just to define where the trace is the flat metric times the correction to the metric tensor, right? That's how we take a trace. Okay. Good. So, now, I'd like to simplify this. And so the way I'm going to do that is to define a new thing, which we're going to call the trace reversed metric perturbation, this H alpha beta. Okay, and I'm going to put a bar on my H alpha beta for that. So H bar mu nu is going to be defined as H mu nu minus 1/2 H, the scalar, mu nu. looks like the trick that we pulled with the Ricci tensor and the Ricci scalar, right? To redefine what, or to define what the Einstein tensor was. Okay? And you could convince yourself of this, but oops, if I take the trace of that guy, that is equal then to H alpha beta, which is equal to minus H. That's why we call it the trace reversed. The traces are reversed. They're minus of each other, inverse of each other. Okay, so now take this and substitute it into the field equation and work that out. And what you get, so this guy over there, where I'm now re-expressing the metric perturbation in terms of the trace reverse metric perturbation, substituting in there, what I get is the following expression: minus H bar mu nu comma alpha alpha minus eta mu nu H bar alpha beta comma alpha beta plus H bar mu alpha comma nu alpha plus H bar nu alpha comma mu alpha, all of that equal to 16 pi T mu nu. A bit simpler than this, but we can now do something. I'm not going to need this again. Okay. We're going to erase it. Okay. So now that I've done that, using the trace reverse metric perturbation, I can pull another trick, which is to come up with a new set of coordinates such that, so new coordinates, just a coordinate transformation, right? I'm free to do this. And the laws of physics should be invariant under such coordinate transformations. And so I'm going to say alpha, x alpha nu, this is some new coordinate vector of my scalar field of events in space-time, is just equal to the old coordinate system of scalar field points, events, plus some vector shift in the coordinates. I'm free to do that. Doing that will change my metric perturbation as follows. H mu nu old minus things that depend on the derivatives of this shift vector, xc nu comma mu. Okay? This is a gauge transformation. So from E and M, it is equivalent. But now, instead of electromagnetism, we're doing gravity. But it is a gauge transformation. And gauge transformations have certain useful properties, right? So for instance, so recall from E and M, for scalar field psi, right? I can add this to the vector potential to make a gauge transformation, right? So if I've got some vector potential A mu, and I want to gauge transform it, it would just be A old mu, minus the gradient of that scalar field, right? I'm free to add gradients of scalar fields to vector fields in E and M as much as I want. I can do it. Why? Why? Because doing this does not change the form of the electromagnetic tensor, right? And so F mu nu, the E and M tensor, is invariant. under these gauge transformations in E&M. By analogy, and mathematically this is true, you could work it out, in our weak field limit of GR, these kinds of gauge transformations tell me that the Riemann tensor is unchanged. So by making this sort of a gauge transformation like this to the metric tensor, the Riemann tensor, which depends on the metric tensor, is unchanged under those gauge transformations. So that is a useful property. So Riemann tensor is invariant under gauge transform. All right. So then, if we choose xc alpha appropriately, right? If we're clever about our choice, we can get the following. The following gauge conditions, analogous to E&M. They are the following: H bar mu nu comma nu is equal to 0. That we might call, again, in analogy to E&M, the gravitational Lorentz gauge. Right? Because I could pick a gauge transformation in E&M that gave me 0 for derivatives of the scalar potential. Okay? Yeah, that's a divergence, right? Okay, so now with this, the field equations become, having made my gauge transformation, minus h bar mu nu comma alpha alpha is equal to 16 pi t mu nu. So by using this, right, I picked the appropriate xc alpha, which made this true, which allowed me to simplify the equation that I have now erased down to this. Should have left that up there. What kind of equation is that? It's a wave equation. This is a wave equation. And solutions to this, looking for solutions of this metric perturbation, involve integrals that look a lot like integrals that you would take in E&M to solve for the potential, right? The appropriate Green's functions and everything are in there. So what this implies is that if you have some stress energy tensor which is generating your curvature and it is moving dynamically, it generates waves in space-time. This is gravitational waves. This is where the prediction for gravitational waves comes from, is the linearized theory of general relativity. And precisely this equation, combined with one other that is the integral that actually you solve for the metric perturbation, which I won't write on the board, it's in the notes. It's kind of amazing, right? Because remember where we started with this. We started in the weak field limit. We started in the weak field limit. But recently, many years after these notes were actually written, or the book was actually written, we've detected gravitational waves now, right? And we've detected them from black holes and from neutron stars and 30 solar mass black holes and 50 solar mass black holes. Gravity is not weak in the merger of two black holes. Gravity is actually just about as strong as it gets in the case of merging compact objects like black holes and neutron stars. But we've detected the gravitational waves, and the prediction for those gravitational waves matches what we would predict from general relativity nearly perfectly. And those predictions are based on a weak field limit derivation of linearized gravity. The thing is, where we were detecting them is pretty far away from the events, right? Where we detected them, the weak field limit applies. And you can actually get gravitational waves from the fully non-approximate, non-linearized GR. You can get them. It's just, this is where the prediction for the existence of gravitational waves came from. Right? And it was even before that we had direct evidence from LIGO that gravitational waves were real. We had cold, hard evidence that gravitational waves were real. Anyone know what that is? Astro people can't say. I know it. I know the astro people know, but any of you physics folk know what the cold, hard evidence for gravitational waves was before LIGO? The Hulse-Taylor pulsar. The binary pulsar, two neutron stars going around each other, and because of their magnetic fields and their rotation, they act like lighthouses, and they're basically the most accurate clocks in the universe. And so we only see their light when it passes, boop, boop, boop. It's like a lighthouse effect. And you can measure that timing. And what gravitational waves predict is for a compact object binary like that, it'll be radiating gravitational waves away, actually because of a quadrupole moment. If you work this out and try to solve it, it's a quadrupole moment of the stress energy tensor. And so the binary should be slowly collapsing together. The period should be increasing. And that's exactly what was measured, almost perfectly. It matched perfectly the prediction from GR, won a Nobel Prize. And so LIGO's Nobel Prize that got Kip a Nobel Prize was not the first Nobel Prize for gravitational waves. It's actually a Hulse-Taylor pulsar. Exempt, you know GR. Now let's solve it numerically. Questions? All right, read chapter 1 of Baumgarten-Shapiro for next week, and I will see you Tuesday. Yeah.
Did you give us another deadline?
Oh yeah. Would another week be enough, or do you want more? What do you think? I mean, you guys tell me. You all tell me. 1 week, 2 at the most. I gotta at least look at the homework at some point. All right. Well, I see much more nods there. Okay. 2 weeks, but there will be another homework for the first chapter of Baumgarten-Shapiro. And the other thing that I'm going to do once I get back from my trip is write up what I want you to do for your first little computational project, because it's just going to be a TOV solver, and chapter 1 of Baumgarten-Shapiro introduces the TOV equations. And so I think that'll be a nice segue. All right.